Okay, this will be the lecture for chapter 43. We'll be talking about nuclear physics, and it's actually pretty straightforward. One of the consequences of this chapter is going to be something we talked about in relativity, where we said that the energy squared is going to be mc squared, quantity squared, plus the momentum multiplied by c squared. And what we can actually do is, I have been lying to you a little bit, we can actually convert some energy or some mass into energy, so energy can be created. It's just in the form of mass energy. So we're going to get the equation E is equal to mc squared, but really it's going to be a change in mc squared. Now what we're going to talk about is we're going to talk about the nuclei of atoms and how they're kind of bound together. There's something called the strong force that I'll talk about. We'll talk about what happens when the strong force breaks down. We have radioactive decay, and essentially what we're kind of doing is we're going to create some energy that's going to be related to a delta mc squared. Talk a little bit about the hazards and medical uses for radiation, and we'll talk about nuclear reactions, fission, and fusion. Something else that we'll kind of also talk about is we'll talk about carbon dating. So how can we actually go ahead and do that? Just a quick shout out to some of the early pioneers in radioactivity, and something I want you to kind of notice is we're talking about the 1900 or so. So what we're talking about today is only 100 years old and change. So we had Röntgen in the 1895, and he discovered X-rays. We had Becquerel. You're going to see a unit named after him, and he actually discovered radioactivity. Rutherford, we've talked about him. He discovered both alpha and beta forms of radiation, and he had that tinfoil experiment that we talked about. And last but not least, we have the Curies, a husband and wife that worked together, and they discovered a whole bunch of radioactive elements, and they were huge pioneers in radioactivity. They both, she actually died from exposure to radiation, and if he was not hit by a car, he would have. But something about her is she was the first woman to get the Nobel Prize, and she got two Nobel Prizes actually, which is extremely rare, one in chemistry and one in physics. Now we need to get a little bit of jargon out of the way, but we also need to clear up a couple things. First of all, when we talk about atoms, we know that we're going to have a positively charged nucleus with some protons and some neutrons, and we're going to have some electrons that are, well, we'll just say that they're in orbit, talking about the Bohr model of the atom. And very often we talk about the total number of nucleons, which is also known as the atomic mass number, and so we could also say this is the number of nucleons, and that's going to be equal to the number of protons plus the number of neutrons. And the number of protons is, of course, the atomic number. That's what dictates what an element actually is. And up until this point, what we've done is we've kind of written, let's just say, one of the most common isotopes of carbon, carbon-12. It's going to have 6 protons. That's what tells us that it's carbon, and 6 neutrons. And we would say, okay, the number of protons is 6, number of neutrons is 6. So we're going to write this as C12 and put a little 6 down here to make it even more correct. So it's going to have an atomic number of 12. Now we could also have carbon, say, 14, which would be like this. Carbon 12, still going to have 6 protons, but now it has an atomic mass number of 14, so that would tell us that it actually has 8 neutrons. Up until this point, you've probably said that the mass of, I'm just going to say carbon 12, is just going to be equal to 12U, which we're kind of defining 1U to be 1.66 times 10 to the negative 7th kilograms. Now, we can't necessarily do that anymore in this class. What we're going to have to start talking about is we're going to have to realize that the protons and the neutrons actually have very, very, very slightly different masses, and the proton's slightly less massive than the neutron by a little teeny tiny bit. This is actually going to be really important when we start talking about decay, because some of that mass is going to be converted to energy. So you definitely want to have these guys scribbled down, and we also know that the electron is about 1,000 times less massive than the proton or the neutron. Now let's just kind of put this in the language of the book. The book defines the nucleon number. Again, I said that's also the atomic mass number, simply with the symbol of A, and that's just the sum of the protons and neutrons in the nucleus. And of course the protons is what dictate what element we're looking at. Now, it turns out that the radius of most nuclei can be given by this simple formula, which is related to the Nucleon number. And this little constant right over there, R0, is simply going to be 1.2 femtometers, and it's a pretty good approximation for the radius of most nuclei. Keep in mind that nuclei are going to have protons and neutrons, and they all approximately have the same density, so they're kind of packed in there more or less with the same spacing and everything like that. Also, kind of translating the jargon into the language of the book, the number of protons, or the atomic number, is written as Z, and the number of neutrons is simply written as N. And so the equation I had a couple of slides ago is simply A is equal to Z plus N. Keep in mind that up until now we have defined 1U to be equal to essentially A minus 1U, but as I mentioned, we're going to start to realize that the protons and neutrons have different masses, and that's going to be really important in a little bit. Just some more jargon. A nuclide is just going to have very specific values for Z and N, and we would talk about different isotopes, which are going to be an element that has the same number of protons but different number of neutrons. Now, I'm not going to talk too awful much about this, but protons, like electrons, do have some spin associated with them, and they are going to have a magnetic moment associated with them. So much like I said, we're going to have an electron that's kind of whizzing around like that, and we're going to have a moment where the protons are also essentially spinning, just like this, and they are also going to have a magnetic moment associated with them. Now, really quick, here's a table that's actually going to be really important for solving some of the homework problems. These are neutral atomic masses for some of the lighter nuclides, and the key word here is neutral, and that means that the same number of protons as electrons. And here we have our familiar hydrogen, atomic number of 1, just 1 proton, no neutrons, and an atomic mass of about 1U, and a mass number of 1. And then we have the first isotope of hydrogen. It's actually called deuterium, and it's still hydrogen. The number of protons is 1. Now it has a neutron added on, and so the atomic mass is like that, and there's the mass number. And then here's a slightly less common version of hydrogen that has 2 neutrons and some mass. And we can pop up to some helium isotopes, and some lithium, some beryllium, boron, 2 flavors of carbon, nitrogen, and oxygen. So we have mass number kind of increasing in that direction right over there, as well as atomic number increasing in that direction right there. Now, I did mention that protons have some spin, and I'm not going to make you do too awful much with that, but just a quick application of that would be an NMR or a MRI, a nuclear magnetic resonance, or a magnetic resonance imaging. And if we were to consider just some hydrogen protons, just like this, they're going to have random spins. They're going to be pointing in pretty much all directions. And that's what would be inside of some tissue that we were trying to look at. And then what we can do is we can insert a strong magnetic field, and we can make the protons all align up with the magnetic field, so just like that. And then we can send in a brief radio wave. And what that radio wave is going to do is it's going to flip the spin of the protons. So they were spun up before. They're going to be pointing in the downwards direction. And when they flip back, they're actually going to emit some radiation. So da-da-da, da-da-da. And what we can do is we can detect those radio waves, and that tells us a little bit about something about the tissue. And what we can do is we can realize that since the magnetic field is going to be different at different locations, and we can also vary the magnetic field in the X, the Z, and the Y direction, and then we can add all those guys together and construct a very detailed image of what's going on inside of your body. And just kind of an aside, if you've ever been in one of these things, it takes a lot of power. These things are power hogs, and they make a horrible noise. It's a wom, 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 wom. And you also need to hold the tissue relatively still for quite a long while as they take a bunch of images to make the final product. Now, let's change gears a little bit and talk about some of the energy that's inside of nuclear bonds. Now, we do know from chapter 37 that energy and mass can be used kind of interchangeably, and when we talk about something called binding energy of the nucleus, what we're talking about is how much energy we need to add to separate the nucleons that are inside of the nucleus. And very typically we refer to something that's going to be the binding energy divided by c squared, which is going to be called the mass deficit. And this is going to look a whole awful lot like E is equal to mc squared. So EB is very often divided by c squared. We can also kind of write c squared as being about 931 mega electron volts per atomic mass. So very, very important for you to have that jotted down. So what we kind of have to do is when we take a look at the binding energy, what this guy is going to be is going to be the number of protons, mass multiplied by the mass of the proton. It's going to be the number of neutrons multiplied by the mass of the neutron. And as I mentioned, these guys are slightly different, minus the atomic mass of whatever element we're looking for multiplied by c squared. And again, we very typically would use this c squared. So let's take a quick look for, let's just say, deuterium, which is going to be this flavor of hydrogen. Let's calculate the binding energy really quick. The binding energy is going to be the number of protons. In this case, we're talking about 1 multiplied by the mass of the proton, 1.007825 multiplied by U, plus the number of neutrons. This is going to also be 1. Slightly different mass, 1.008665 multiplied by U, minus the mass of deuterium. And if you flip back to the last table, you're going to see this is going to be 2.014102. Keep all the sig figs on this guy, multiplied by U, and we go ahead and we multiply this guy by c squared, so 931.5 mega electron volts per U. You're going to see that the U's are going to go away, and we're going to have the binding energy being equal to 2.224 mega electron volts. Now if we were to go ahead and plot say the binding energy divided by the number of nucleons, and actually let's go ahead and calculate EB divided by A for deuterium. Deuterium is going to have 2 nucleons, and so it's essentially going to be this binding energy, E sub B, divided by 2, and that's going to be 1.112 mega electron volts. Now, and this is kind of how hard it is to rip those nucleons apart. It would kind of make sense that as you add more and more and more nucleons, so as we were to go in this direction when we're talking about A, that it should get stronger and stronger and stronger and stronger. And actually it is. It's kind of interesting. We're actually going to have a spike for helium, which is very, 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 very stable. And as we would expect, we're going to add more and more and more nucleons, and it's going to become harder and harder and harder to separate them. I'll talk about why in the next slide. And actually we're going to reach a peak at nickel. And at that point we've kind of hit saturation, and we're going to start to have interactions between protons inside the nucleus, and that's going to slightly weaken it. And so it's going to become slightly less stable as we work our way to higher values of A. So a quick look at example 43.3, and this is going to be taking a closer look at nickel, the most strongly bound nuclei. So nickel is 6228 Ni, and it has an atomic mass of 61.928 blah 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 U. And we can calculate the binding energy pretty straightforward. We know that Z is going to be 28. That's going to be that number right over there. We have the mass of the hydrogen, and we know that there's going to be 34 neutrons, and that's just A minus Z, so 62 minus 28. The neutrons have a slightly different mass, and we were given the mass of nickel. And so all we're really doing is we're doing the same thing I did on the last slide, calculate the mass deficit. Sometimes we will just write that as a delta M. And so delta M is going to be equal to Z multiplied by the mass of the hydrogen plus N multiplied by the mass of the neutrons minus the atomic mass AZM. So very often we'll see this written as the mass deficit, delta M. You go ahead and do that, and it's going to be 0.58 multiplied by U, multiply that by C squared, and we're going to end up with a rather large number, 545 mega electron volts for nickel. Now, related to binding energy is something called the nuclear force, and essentially it's going to be what holds the nucleus together. And if you think about it, if we just had a simple atom where we had a positively charged proton, we have an electron way out here that's kind of orbiting it, the electron's held in by the electrical force. And what would happen if we added a second proton right over here? You might have said to yourself, wait a minute, I know that these are opposite charges. They're going to tend to be repulsed by each other. That's the electrical force. Turns out that we need to add a neutron, and adding a neutron is going to give us the nuclear force. So go ahead and put a neutron right over there, and that's going to provide a very, very strong force, and it's actually called the strong nuclear force, and it's actually much stronger than the than the electric force. So it's the neutrons that hold the protons together, and to make it even more stable, we even tack on another neutron just like that. Keep in mind the nuclear strong force does not depend on charge, and it operates in a very, very, very short range, and so, a couple of femtometers. So on the order of the nuclear, the size of the nucleus. Because it's a short range, nucleon's only going to interact with those that are closest to us, and that's going to be important for stability when we talk about larger and larger and larger nucleuses. And also it does favor pairs of protons and pairs of neutrons that tends to have opposite spin. So think about a pair of protons and a pair of neutrons each having opposite spins. This also explains why helium was one of the most, had that little spike on the previous slide. Just kind of a diagram here of what's holding the nucleons together. If I had two positive charges right over there, and I were to hold them really, really, really close, there's going to be a strong repulsive force. If I were to add in, say, a neutron, just like this, then I'm going to get a strong nuclear force that is actually going to be attractive, and it's going to be stronger than the electrical force. However, keep in mind that as I were to separate these guys by a larger and larger and larger distance, the nuclear strong force is going to go down, so it's going to be very insignificant. So it operates only on a very short range, and we still do have the repulsive electrical force. And as I mentioned, it does matter how close we are, and the strong force is far more effective for smaller nuclei. So picture this guy right over there. It's got 3 protons and 3 neutrons. The nucleons are very close together, and so the strong force is quite strong. We start to hit saturation when we have nucleons further apart. So picture this guy right out there. This could be like uranium or something crazy like that. Tons of protons, tons of nucleons. Here the nucleons are very far apart, and so this guy tends to be less stable and is far more likely to decay than that guy is. One thing to kind of keep in mind is that neutrons by themselves are actually radioactive, and they tend to decay. Actually, they have a lifetime of about 15 minutes or so, and what they will do is they will spontaneously transform into a proton and electron. So here we have a neutron, and this guy is going to essentially spit out a proton and electron. So we could actually even kind of write this as that's going to decay spontaneously into a proton and an electron. And I am lying to you a little bit. It is going to also spit out something called an antineutrino, which we'll see next chapter. So for right now, don't worry about that too awful much. Keep in mind that if you were to take a look at the masses, you could say to yourself, wait a minute here, these guys don't add up. The mass of the neutron is not the mass of the proton plus the mass of an electron. And you're right, some of that mass does go into energy. It's going to go into kinetic energy largely of the electron as the electron spits off in that direction. Also keep in mind that momentum is conserved, so the proton is going to slightly recoil in that direction, and the electron is about 1,000 times more massive, so it kind of goes whizzing off in that direction. The proton goes in that direction. So a neutron needs protons around to keep this from happening.